Welcome back everybody for the new colloquium. Today's speaker is Simone Brugiapaglia. He got his PhD from Politecnico di Milano, and he did postdocs in Lausanne and in Simon Fraser in Vancouver before joining Concordia in 2019. Among his many distinctions, we can name the postdoctoral fellowship from the PIMS Institute and the Leslie Fox Prize for Numerical Analysis at the 19th IMA. And today he's going to talk about the mathematical foundation of deep learning, from writing impossibility to practical existence theorem.
All right. Thanks, Giovanni, for the beautiful introduction. And most of all, thank you for inviting me to this colloquium. It's really an honor to talk here. So yeah, before we start, I would like to acknowledge my collaborators on the projects that I will present today. So Matthew Liu is a former undergraduate student at Concordia. Nick Dester is an assistant professor at Florida State University. Ben Upcock and Paul Tupper are professors at Simon Fraser University. They were my postdoc mentors there. Sebastian Moraga is a PhD student at SFU, and Clayton Webster is a distinguished researcher at the University of Texas at Austin. Let me just start by acknowledging sources of funding that make this research possible over the years since my postdoc up to now. So ANSERC, Concordia Faculty of Arts and Science, the CRM, so thank you, CRM, and the PIMS Pacific Institute for the Mathematical Sciences. So maybe you've seen the sentence in my introductory slide. Get ready to delve into the mind-bending intersection of mathematics and artificial intelligence, where elegant equations and concepts lay the foundation for the miraculous advancement in deep learning that are transforming our world today. And you can see that there are quotes in this statement. So that's not my sentence. It's a quote. Can you guess who's this quote from? Have you ever heard anything similar?
ChatGPT.
Yes. This is a quote from ChatGPT. I asked ChatGPT, write a brief opening sentence for a seminar on the mathematical foundations of deep learning. Make it exciting and mind-bending. And that's the output. Pretty stunning. Huh? So I was really happy with the output. And I'll say, okay, I'll put that in one of my slides and ask the people who they think wrote this. So we live in a time where AI is literally at our fingertips. We can chat with ChatGPT, the conversational engine that is based on machine learning. And it's having a profound impact on many sectors in industry and, more importantly, perhaps for us in academia. If you go to this website, the 2022 AI Index Report by Stanford, that's a website that collects a lot of data and statistics about the evolution of the AI field. So this is the number of publications per year from 2010 to 2021. You can see in the topic of artificial intelligence. And here you have to multiply by 1,000 this number on the y-axis. So in the last, from 2017 to 2021, there's a steady increase. Of course, AI is a very topic, so you should kind of split it up into subtopics. And that's what this other plot is aiming to do. So here there's pattern recognition, machine learning, computer vision, algorithm, data mining, and so on, all the subfields of artificial intelligence. You can see the light blue line that has the steepest ascent here is machine learning. So the amount of literature being produced here and the research is really mind-blowing in the past few years. And we have seen the impact of deep learning, in particular within machine learning, specifically the technique called deep learning that I will tell you more about in different fields. I've shown you now ChatGPT. Deep learning is one of the crucial ingredients that makes that conversational engine possible. Up to Tesla, so self-driving cars, or you can, if you want to play Go, now the AlphaGo will be really, really tough to beat. And it's also based on deep learning when you get recommendations from Netflix and so on. So we see a widespread impact of this technology. We also have seen computer scientists, 3 outstanding computer scientists getting a Turing Award for their contribution to deep learning and their impact in 2018. One of them is, Yann LeCun, Geoffrey Hinton, and Joshua Benjo. One of them, of course, is the head of Mila, a member of the CRM. We're quite proud of this achievement. And so that's the picture we are in. So there's a lot of breakthroughs being made and recognition and celebration of this field. The field where I come from originally, which is numerical analysis, computational mathematics, is also being impacted by deep learning. So there's a lot of papers. For example, here there's 2 PNAS papers, Science News article, talking about using deep learning in different ways to solve challenging problems from computational math, like solving partial differential equations, or, for example, discovering a dynamical system from time series data. So the impact is really pervasive. However, like in every story, there's the other side of the coin. There's a lot of skepticism as well around deep learning. There are a lot of concerns. Here, I'm reporting some articles like published in kind of journals for wide audiences. For example, people talk about instabilities of deep learning. They're due to the so-called adversarial attacks. These are attacks that can craft small perturbations of the input that lead to huge distortions in the output. And this is a concern. This is an instability of these algorithms. Then can lead to big concerns, for example, when you want to apply deep learning to a self-driving car that might maybe not recognize a stop sign and go ahead, or if you want to apply deep learning to reconstruct a medical image or to produce a diagnosis. So there's big concerns. And so for us as mathematicians, there's a little mission here. We should kind of use our skills and our knowledge to understand how these algorithms work, in their inner workings of these algorithms. And that's actually what's happening. A huge amount of people in the mathematical community is tackling tough questions in deep learning to understand how these algorithms really work. But this is not a new trend. We can go back to this paper by Stephen Smail in '98, Mathematical Problems for the Next Century. So Smail wrote this paper in request to Arnold, that was at the time the vice president of the International Mathematical Union, who asked mathematicians to write lists of open problems that were relevant for the community for the 21st century, inspired by what Hilbert did 100 years before. And there are 18 problems in Smail's list. The 18th is limits of intelligence. So that's the last problem. It's a really broad one. And the question is, what are the limits of intelligence, both artificial and human? Of course, it's a huge question. But what I really like is this quote, where Smail calls for a broader study. So a broader study is called for, one which involves deeper models of the brain computer in a search of what artificial and human intelligence have in common and how they differ. I would look in a direction where learning, problem solving, and game theory play a substantial role, together with the mathematical numbers, approximations, probability, and geometry. So what I like of this quote is that Steve Smail is hoping for a highly interdisciplinary approach, different areas of math that come together to understand intelligence, and in particular for this talk, artificial intelligence. And that's what happened. That's what I think was particularly visionary to write this at the time, because that's literally what's happening these days. So, okay, I've been talking about deep learning for a couple of minutes, and I will tell you what it is, and I'll tell you now about the structure of the talk. So, because the focus will be to understand both the potential and the limitations of deep learning. Yes, yeah. Question. I would like to understand both the potential and limitations of deep learning through rigorous mathematics. So that's the broad goal of this talk. And of course, that's a huge question. There's a lot of activity. There will be a whole course would not be enough to understand what's going on in the area. I will do that through 2 specific case studies that I was involved in my research recently. And they will have 2 different flavors. One is so-called impossibility theorems. And that will be results where we investigate the limitations of deep learning. We will try to quantify precisely when deep learning is not able to do something. And that something will be a precise task, that is recognizing whether 2 objects are identical or not. The second part will be more on the positive side, so practical existence theorems, understanding the potential of deep learning in the task of approximating functions of many variables, so high-dimensional functions. So, okay, I need to tell you what deep learning is, otherwise it is going to be difficult to explain the theorems. So it's hard to get an orientation. There's a typo. Getting oriented amidst the deep learning literature is tough. If you go to Google Scholar, you type deep learning, you'll find more than 5 million articles it's a jungle, literally. It's not easy to find your way through it. These are two, if you're curious, kind of to get an introduction, or if you're a student who don't know where to start. For mathematicians, I highly recommend this Science Review paper, Deep Learning, an Introduction for Applied Mathematician. That's a very gentle and kind of formal introduction, step by step, to the field, written by Catherine and Desmond Hayem. If you're more interested in historical remarks, there is this very comprehensive historical review of deep learning by Schmid-Huber. So what is deep learning? First, to define deep learning, we need to define the objects of deep learning that are neural networks, deep neural networks. Deep neural networks at the beginning were algorithms inspired by trying to model how the human brain works. So a network of neurons with links between them. But mathematically, you can think about neural networks simply as function approximators. So specifically structured function approximators. You start from an input x, and then you apply an affine transformation A0. Then you have nonlinear so-called activation, which is a nonlinear function. You apply that component-wise to your vector A0 of x. Same, another nonlinearity, and so on. You do that d times. Typically, the last step, you don't do the linear activation, the nonlinear activation. And that's how you construct your so-called deep neural network, okay? So each of these sigma aj, hj will be called a hidden layer, because you can visualize this type of algorithm as a sequence of vectors. Okay, you have the input vector, which is the input layer, and then you propagate somehow the information to the first hidden layer through this transformation, and you can design links from neurons. If you think about neurons as the entries of your vectors, you can think about the links as the non-zero entries of the corresponding matrices that define the nonlinear activation, the affine transformation, okay? So that's kind of why you will see a lot of graphs when you look for deep learning. But honestly, in terms of mathematics, we need this. This is more useful, okay? That's what actually a deep neural network is, just a composition of affine and nonlinear transformations. So there's a bit of jargon here to learn. Sigma, typical activations that people have considered. So the idea here was to activate or not a certain neuron. So for example, you can do that with a so-called ReLU function, which is a rectified linear unit, which is just the max between 0 and x. You can do that in a smooth way, like with hyperbolic tangent, or there are other options. And there are names that we need to be familiar with. So hidden layers, as I told you, the output and the input layer, and the depth. So we say deep learning because the depth d, we count the number of layers that we propagate x through, and that will be the depth. So why learning? What are we learning here? So this is a learning model. So sigma, the activation will be fixed. However, the coefficients, the matrix and the vector defining the affine transformations will be so-called trainable parameters. These will have to be found through a suitable optimization problem that will kind of try to make the network fit a certain given set of data. So I will denote this, all the trainable parameters, we'll put them on a big vector, capital theta, and assume that we are in RT as the dimension of the trainable parameters. And then your network is essentially, you can think about it as a parameterized family of functions, phi of theta, where the parameters are trainable parameters. So we know what a deep neural network is. What is deep learning? Well, now we need to do the training. So we give it a data set, xi, yi, and we train the parameters. So we find the optimal parameters defining the network by minimizing a possibly regularized loss function. So what the loss function does is kind of measures the goodness of fit of your model, the network, to the data. And you have different options here. For example, in the classical regression setting, you might have a least squares loss function if it's just a sum of the absolute squared residuals. If you are in the so-called classification setting, then you can have other options, such as the so-called cross entropy loss function. And then you might want to promote some extra amount of structure in the trainable parameters through regularization. So for example, the regularizer term could be some norm of the trainable parameters. For example, the L2 norm that will shrink the parameters, will not then grow too much, or the L1 norm that will promote sparsity in the parameters. So will tend to promote many vectors where there's many zeros. All right, how we do solve this? This will be a very tough optimization problem to solve, non-convex, highly nonlinear. So in practice, you will have to perform some numerical optimization. Typically, large data sets. So what's very popular, and now it's almost a classical technique, is stochastic optimization, in particular stochastic gradient descent. So that would be one possible technique to optimize that regularized objective function. How does it work? Well, typically your data set will be very large. So you split it in a bunch of so-called batches. So now you have smaller sets of data sets of data that constitute a partition of the whole data set. And you focus in your loss function, instead of considering all the data here from 1 to m, you only consider the data in the batch bj. And therefore, you optimize with a gradient descent step by going towards the direction of steepest descent. You just optimize this way, okay? And you iterate through the batches. I know number theorists in the audience. I was proud to have a mod here. That's the only number theory thing. But you just, you alternate between all the batches and you revisit them. And whenever you touch all the batches, that's called an epoch of training because you have explored the whole set. All right, so that's about a crash course on deep learning. So you know a bit of the jargon, what we're going to talk about. So the first part is about rating impossibility theorems. So exploring the limitations of this machine learning technique. But before, maybe, is there any question about the setting? Any question about deep learning in general? All right, so let me start with the first research project, and that will start with a question for you. Okay, I'm telling you now that the green words, AA, GG, LL, MM, are good. And the red words, AG, LM, GL, MA, are bad. Now I'm asking you, is YY good or bad? And is YZ good or bad? So who thinks, and you can type, if you don't like, you can type on the chat, who thinks that YY is good? In the room, everyone thinks YY is good. What else? I don't know in the chat if there's any debate going on or people are there. Okay, we'll see. People have not opinion on the YY. Who thinks that YY is bad? Maybe everyone thinks that it's bad. No one? Oh, here, that's something going on in the chat. Okay, someone thinks it's not good, YY is good. But the vast majority thinks that YY is good. How about YZ? Who thinks that YZ is good? Who thinks that YZ is bad? All right. Yeah, okay, so the almost totality of the audience thought that YY is good and YZ is bad. So for humans, this is a quite simple task. That's what it is. So here we were trying to spot I don't know how to close this chat. Let me see. You can close that maybe? No, because I don't see that. Perfect. Okay, thank you. YY is two identical letters. YZ are not identical letters. So for humans, it's quite easy to generalize this kind of structure, even though, so that was your training set. I showed you letters, only A, G, L, M, and combinations of these letters, but there was not Y nor Z in the training set. Therefore, you were able to, so to speak, generalize this task to previously unseen examples very easily. The question is, can algorithms do the same? So can deep learning generalize this type of task as easy as we can? Already I see some people think that no, it's impossible. We'll see. The question, it will be, I mean, the answer will be, it depends. So studying this type of question at the beginning, when we started this project with Paul Tapper and Matthew Liu, it was about motivated by cognitive science. So in particular, in linguistics, for example, to understand, so understanding, kind of recognizing this kind of patterns in words can be useful if you try to understand if a certain sentence is grammatically correct or not, or if a certain word is possible in a language or not, okay, if certain structures are there or not. In 1999, Gary Marcus showed that 7-month-old infants can generalize outside the training set this kind of patterns, like the identity, or more difficult. So the experiments were like, they were with sound. So they were, infants were listening to sounds like TTK or KK2, and they were supposed to generalize to new sounds, just focusing on the pattern. And so it's possible for humans, even very, very young humans. And that led to a huge debate in the cognitive science community. People who thought, well, sorry, but then also Marcus showed that neural networks cannot generalize this kind of task. That was in '99. So the algorithms that were used at the time were not, of course, the state of the art, but at that time, it generated a huge debate. So now people who thought that this was kind of supposed to show that the human brain is not just a neural network, there's something else going on in the brain that has nothing to do with a network. Maybe there's some algebra-like structure in the brain that is not just neurons linked together. Or some others that thought, well, no, this is just a problem of how the networks are trained, so the brain is actually a network. And if you were in this side, you were called a connectionist. Otherwise, you were not a connectionist. So there's a lot of back and forth in the literature about this debate. Even recently, there's a debate about Joshua Benge and Gary Marcus, not exactly about this theme, but they touch upon similar questions and the future of AI. That happened here in Montreal. So I invite you to check that out. It's quite fun. So we want to tackle this problem in a rigorous sense. So we need to set up some notation to understand if machine learning and deep learning in particular can generalize this kind of identity effect. So calligraphic X will be the set of admissible inputs. R will be the rating given to a word. So for example, 1 if the word is good, or 0 if it's bad. And X in our example was the set of all 2-letter words, and R was a number between 0 and 1. The probability that that word is good or bad. The training set in the example I showed you at the beginning was this. So I showed you these letters and told you these were good, so 1, and these other, words, these were bad, so 0 ratings. And then there will be the learner that we will model in this way. The learner will be a generic function that, given a data set D and a new input X, will have to assign a rating. Okay, it's just a function transforming the data set and the new input into a probability. And this could be, for example, it could be a natural rating the set. Like that theorem that claims something of this scenario, for example, when L is actually generated by a deep network. So first, there is a very general result, so general that might look almost useless. So the result goes as following. If I give you a data set D and a transformation of the input space, it's just a function at this stage, going from X to X, such that the data set is invariant to that transformation, then the following will happen. Any learner that is invariant overall to this transformation, that is, if you transform both the data set and the new input with tau, the learner doesn't notice, then this learner will never be able to distinguish tau X from X. We'll always assign the same rating to these two potentially different inputs. And there's pure mathematicians in the audience, so I ought to have a proof at least. There is a proof in the talk, and it's a one-line proof. It's the shortest proof I've ever published. We're really happy that we did that. It's one-line proof. And it's almost a tautology, honestly. Like, you start from LD tau X, you use the invariance of the data set, so you replace D with tau D. You now use the invariance of the learner, and you get rid of tau everywhere, and you get the, okay, that's it. So this might seem like, again, what do we do with this result? Like, this is so abstract that it doesn't tell me anything in practice. So the question now is, can we actually apply this? Can we find a framework that is relevant in practice, where the learner, for example, comes from deep learning, trained with FGD, and an actual transformation that works for the problem we're studying, the identity effect? So these are the questions that we need to answer to apply this result and make it a useful result. So it turns out that it's possible to apply this result in this framework that is quite close to what people actually do in practice. So now we're given a data set, again, input words and ratings, and we assume to have a model of this form. So this is more general potentially than a neural network. We're assuming to have a model of the form phi v wx, comma wx. So the important thing is that x should first be multiplied by a certain matrix W that is trainable. And then other stuff could happen. Could happen things like propagating the signal through the network, or even you can come up with other models after you multiply the input by W, as soon as you can write the whole model in this form. So if that happens, and that happens in particular with neural networks, feed-forward neural networks, independently of the number of layers, if you train such a model, as I showed you before, with SGD, in particular with k iterations of SGD, okay, you stop after k iterations, and you train to minimize this objective function where there is any loss function here, as soon as the whole thing will be differentiable. That's the only thing you need, because to have a theorem to apply SGD, even though in the case of non-differentiability, you can replace gradients with a subgradient, so you can generalize this kind of thing when you don't have beyond the differentiable case. But for simplicity here, I'm presenting the setting. So any loss function f, and as soon as the regularization term acts in this way, so that's the key part. You're not allowed to regularize in any possible way, but you are allowed to regularize the input layer, W, only using the Frobenius norm. And you can do anything on the remaining, the remainder of the training parameters, okay? RV could be anything, again, as soon as you have differentiability. Okay, so you minimize that loss function with k iterations of SGD. And also we need to initialize, whenever you have an iterative method, you need to pick an initialization. Typically in practice, you randomize the initialization. So as soon as the random initializations of V and W are independent, and W is essentially invariant, the distribution of W0 is invariant to right multiplication by T. As soon as this happens, then you have that the learner defined by training this model with k iterations satisfies the invariance property. And also, sorry, I haven't told you about the transformation T. So what is T? We need to write T with respect to X here. It's a generic space, but now we need tau to be linear to apply the theorem. And if it's orthogonal, then everything goes through. So just a comment that this assumption is kind of reasonable. For example, in practice, you might initialize with all the trainable parameters, IID, random Gaussian variables. And for example, if they're centered, then this invariance happens. Okay, the random Gaussian vectors, with center unit variance, if you apply an orthogonal rotation here, that will be invariant. So that's kind of the first step that we need. We can prove formally the invariance of learners built in this way. And this can be generalized a little bit. So for example, you can consider models that take, these are, for example, sequential models or recurrent neural networks. They take the letter of the word, they feed it through the same input layer. So this model is not the same as this. Now you have X and Y, which is like, the meaning is slightly different. There are two different letters of a word. So you can generalize to learners, to models of this form, and also to other training algorithms, such as ADAM. It's very popular. It's called adaptive moment optimization. And so that's one piece of the story. We can prove formally invariance of the learner in this scenario. But now let's go back to our initial problem, the identity effect. So I was giving you two-letter words. So what could be tau that does the job here? Let's consider this particular tau. Tau operates as follows. Remember that in the training set, I never showed you Y and Z. So in this problem, the training set will contain examples that never see the letter Y and Z. Now, tau will operate as follows. It will change the second letter. If the second letter is Y, then we'll switch it for a Z. If it's Z, it will switch it for a Y. Otherwise, it will just do nothing. So of course, the training set here doesn't contain Y nor Z. Therefore, if you apply tau to anything in the training set, it will do nothing, because it will never operate on the second letter. It will never operate on any letter. So now the question is, how is this transformation corresponding to an orthogonal? Well, now we have to be careful. That depends on how you encode letters. Now we're talking about letters, but there's just, I'm hand waving there. Like we need to define letters formally as vectors in order to give them as input to the network. So you could encode letters, for example, as vectors in R26. And depending on which encoding you use, tau will be represented with a matrix with certain properties. So it's a little in an algebra exercise, for example, if you use the so-called one-hot encoding, where A is just the first canonical vector, B is the second canonical vector, and so on, T will just be a permutation matrix. So tau will be represented by a permutation matrix. If you use any orthogonal basis, then T, the matrix representing tau, will be an orthogonal matrix. So in these two scenarios, we can apply the theorem. So if you encode letters in these two ways, either one-hot encoding or orthogonal basis, then essentially you will be stuck with invariance of the learner, no matter how many iterations of SGD you do, no matter how deep your model is. However, if you only have linear independence, well, in that case, T is only invertible. There's no orthogonality. So the impossibility theorem doesn't apply. This doesn't mean that you will be able to generalize. So we're not able to prove impossibility. So depending on the encoding, we might have different scenarios. And now, so this shows that the encoding under the first two scenarios will be invariant to tau. Therefore, the LD tau x will assign the same rating, sorry, L will assign tau x and x. Now let's make a choice. So for example, if the word x is yz, then tau x, again, apply that transformation, it will switch z with a y, so now it becomes yy. So now tau is changing from bad to good. So in particular, the learner will be always stuck in classifying yy and yz with the same rating, no matter, again, how much you train, how much depth you have. So we'll be provably unable to generalize outside the training set. So we validated, so that's the theory. We validated the theory with some numerical examples and also try to see what happens beyond the assumptions in the theory. So from here, there's different scores assigned to different letters, different words, sorry. So the first column is the rating assigned to the word AA. The second column is the rating assigned to, so here's a bit of a technical issue, it's the first bad word in the training set, which is, we denote here as little x, little y. And then so these first two columns measure the performance of deep learning inside the training set with examples that it has seen during training. And the last 6 columns measure the performance outside the training sets. Okay, so with examples that contain y or z. And so again, the rating, so ideally you would like to see a pattern here. And now we change the encodings here from top to bottom. Top line is the one-hot encoding. In the middle, we have the Haar encoding. So that's an orthogonal encoding randomly generated according to the Haar distribution. The third line is the so-called distributed encoding. So this is done by activating, in this case, 3 random bits to represent each word, each letter. For example, A will be zeros and 3 ones in random positions. B will be zeros and 3 ones in other random positions. So in this case, we don't have orthogonality. We only have linear independence with very high probability. And we can see that's the only case where outside the training set, we start observing certain patterns. Okay, so for all these 2 first rows, and so if you move from left to right, we are increasing the depth. So this is depth 1, 2, 3, for example. Well, we tried more, nothing changes. You only see the emergence of a generalization when you break the so-called orthogonality barrier. Okay, so this kind of numerics shows that deep learning, although it's a highly nonlinear technique, is not able to break this orthogonality through training. There was a question, I think, related to this. Let me see. How do you choose the encodings? Can you give an example of real data sets? Yes, actually, the next slide would be an example. So here the encodings are just letters encoded with either one-hot, orthogonal, or distributions of random bits, like the distributed encoding. The next example is so-called MNIST data set. So now we are trying to classify, instead of pairs of letters, pairs of numbers. And more than that, pairs of handwritten digits. So pairs of images that correspond to handwritten digits. That's the so-called MNIST data set, very popular as a first benchmark in virtually any machine learning method. So now it's a bit more complex because first we need to recognize the image. So we apply computer vision model to essentially a 9 or an 8 or whatever, or if the other image here could be a 3 or a 5. So a first step is a deep learning model that aims at classifying each image. And then we train another model, the identity effect model, to understand if they are the same digits or not. So as before, we don't show all the digits to the training set. We hide 8 and 9 from the training set. And then we would like to generalize, in this case, to see if a number is palindromic or not, if it contains 8 and 9. That was not shown before upon training. So now the setting is a bit different. So you can think about this first computer vision step. This will transform an image, which is the input, into a probability vector from 0. So the output here is a 10-dimensional vector that assigns the probability that that image is each digit. So for example, this is recognized as a 9 with very high probability, for example. There's a high bar here. There's uncertainty between 3 and 5 in the example. So now somehow the encoding is given by the computer vision model. So the computer vision is transforming the set of pixels into a 10-dimensional vector, which is not an encoding like we considered before. Like it's not a one-hot encoding, it's not an orthogonal encoding, it's not a distributed encoding. It's sort of a noisy one-hot encoding, because like when you're really certain that a digit is, for example, here, 9, then you will have a very high superposition and a very low another. You might be close to be distributed when the classifier is not uncertain. It's uncertain about what to do. So here, the quality of the encoding will be determined by how much you train or for how long you train the computer vision model. And now we do two regimes. First, we stop the training of the computer vision model very early, so-called under-trained model. So the computer vision model will not do a great job at classifying individual digits. The second scenario will be an optimally trained computer vision model where we do as best as we can. So the computer vision will do a great job at classifying individual digits. And then we give the respective outputs to the identity effect model. And as before, now, interestingly, you can see again that the top row is the under-trained model. So now let's just focus on the last 6 columns. These measure the performance outside of the training set, where there could be 8s and 9s in the number. So the top row, the deep learning is able to do a better job at distinguishing palindromic from non-palindromic numbers when the computer vision model is under-trained. Instead, when you optimally train or overtrain here, although we should say optimally train the computer vision model, it becomes more difficult to understand if there is an identity or not there. So from a kind of philosophical perspective, or almost, you can think the computer vision focuses on the details. So it's good at kind of classifying one single image. Instead, the identity effect model focuses on the big picture, the pattern. So if you do very well on the details, you're going to miss something on the big picture. On the other hand, if you maybe a bit sketchy on the details, but somehow that helps finding the big pattern. So that's what's happening in this. Again, it's a toy model, toy experiment, but we were able to observe this, that is what was expecting. And mathematically, that happens because in the overtrained or optimally trained case, the encoding is closer to a one-hot encoding. So that's formally why this is happening. Okay, so that's a good point to start questions. So I'll take questions about the first part, and then I'll change topic for the last part. So any question so far or online? Right. So keep in mind, I'm overtraining only the computer vision. So here, overtraining only refers to the model that recognizes the digits. So if you overtrain this model, the probabilities will be closer to 1. So the encoding will be closer to the canonical vector basis, which is not good for generalizing. Instead, if you undertrain, there will be more noise here, but that noise will help you generalize the pattern. So that's kind of the intuition behind it. There was a question? Yeah.
So orthogonality is the enemy.
Sorry?
Orthogonality is
orthogonality, yeah, is the enemy here of the encoding. It's kind of a barrier that is not possible to break, at least with SGD and with that setting.
In the daily life in Turkish language, it means that for a baby, the more we see possibilities, the more we can find similarities between some stuff. So the baby is the equivalent in the metaphor of the really not well-trained.
Right. Yeah, that's a beautiful one. Yeah. So if you think about a baby as an undertrained model, yeah, the baby could see more things than we do. Yeah, that's nice.
There's also some
I will steal this in next talks.
effect, which is like the more you see possibilities, the more you can, the less other possibilities.
Right. Yeah. Yeah.
But how come we can still have a same performance as a baby on those tasks? How come there is not any decision algorithm that goes from a threshold from simplicity to the bigger pictures to the more?
Yeah, these are big questions. I have no idea. I don't want to. It's yeah. I mean, this is more kind of honestly a cognitive science question. If you think about the human brain, that's where I stop. Like this is a model that tries to say something about deep learning. Now there's a question of, is deep learning a model for the brain? That's another debate. Assuming that deep learning is a model for the brain, that maybe this theory tells you something about the brain.
Because in perception, there's something called Gestalt, which is the totality is more important than the sum of its parts.
Right.
And how come that in the parsimonial way, how come that the mathematical function didn't grasp this notion of the bigger picture is more important than the sum of its parts?
Yeah, I have no idea. That's a deep question. No, we're happy to talk about this later, but I've nothing to say on the spot. It's a really deep and philosophical question. Other questions? Or maybe there was something in the chat. First line in the plots in the model at the first epoch or the one at the 12th epoch. Yeah, sorry. So here, if we zoom in a bit, I don't know if I can zoom in a little bit. Yeah. So this is the training history of the computer vision model. So the undertrained model is stopped as one epoch, this one single epoch, and then we stop. The optimally trained, or we should have called optimally, not overtrained, because we pick the best test loss. So 12 epochs, that gives you the best test loss in this history, then it starts increasing. So these are two, in terms of which line is which. So the undertrained here, I'll never be able to go back to, yes, okay, maybe, yes. So the undertrained here is top row. So you see one epoch here. For the computer vision model, you train one epoch. On the top row, you train 12 epochs, the computer vision, the bottom row here. What happens to the orthogonal behavior in this asymptotic regime, both in the data and model size? Right, so this is, honestly, there's nothing, you might have seen here that there's no, in a way, there's no, in a way, there's not the statistical viewpoint that is usual, like maybe we're trying to see generalization as kind of be the training sample is picked from one distribution, and then the out of training samples are taken from another distribution. We don't get that perspective here. So it's kind of different from the usual statistical learning theory stuff. But so here the dimension is fixed. There's no, this is a fully non-asymptotic theory. Okay, so there's no, I'm not sure what happens asymptotically. Let's say if you the amount of data going to infinity, maybe that's a good point. I don't know. We haven't thought about that. That's a cool question. Thank you. All right. So how much time do we have, Giovanni?
Yes, take 15 minutes.
15? Okay. I can do it. So I'll be a bit faster here. Second problem is different flavor. So here we want to quantify the potential of deep learning in another task, which is approximating a function of many variables, given pointwise samples. So that's classical function approximation problem. And there's many applications. I mean, there's a super general framework with many applications, in particular in the study of parametric differential models that people care about in engineering when they model a variety of phenomena such as weather, climate, and so on. And typically you want to build an approximation of this function, which might be a black box model. So maybe you put together a big weather simulation. So you give the parameters to the model, and then you have an output, maybe a quantity of interest, what's the temperature at this place in 2 days' time. And you would like to build a surrogate to that function. So something that is much faster to evaluate instead of running the whole simulation, and hopefully accurate too. So the classical idea here is if your function is smooth enough, then you might want to approximate it with orthogonal polynomials, such as Legendre polynomials. So let's say that you typically in real models, you have high-dimensional functions, so you have d variables. And let's say for sake of simplicity that our domain is the unit or just the hypercube minus 1, 1 to the d. We tensorize Legendre polynomials over that hypercube, and we get an orthonormal basis for L2. We expand F into that basis. You know, we are in Hilbert space. Everything is great. We can just do inner products to get back the coefficients of the expansion. And we want to have an efficient or a parsimonious surrogate. So typically, you want to build a sparse approximation in this polynomial basis. That means that you only want to activate a few coefficients in this expansion. So the so-called norm 0 here of the coefficient vector should be small. That is much smaller than for example, an ambient dimension that you pick when you truncate the polynomial basis. Or in general, you don't want to activate too many coefficients. So here, I'm tensorizing the Legendre polynomials. Okay, so these are the 1D versions, and these are the tensorized 2D versions. For example, you have to think that, so I will use, I knew that would happen. Okay, I'm back. This is 1D. No, it's too dangerous. Let's try slower. Okay, so 2D Legendre polynomials, and this is the index space. Okay, so 0, 0 means you tensorize constant against constant. 1, 0 means linear against constant, and so on. Okay, so when I'll show you plots like that, I'm thinking about tensorized polynomial, but in the index space. Okay, careful, good. So you can give rigorous theory for when this kind of sparse approximation works well. And precisely if your function is smooth enough, that is holomorphic when it admits an holomorphic extension to a so-called Bernstein polyellipse of a certain size. So that's a classical object used in approximation theory. At least in 1D, it's very classical. In multi-D, it's more recent research that led to beautiful results quantifying the approximation rate for this type of sparse polynomials. So if F admits an holomorphic extension on a Bernstein polyellipse of size rho, then you can exactly quantify the decay of the so-called best S-term approximation error. That is the best polynomial approximation you can construct using Legendre polynomials and activating only S-terms. And you can show that this scales exponentially in S to the 1 over D. So there are also other types of decay bounds. For example, you can show an exponential, an algebraic decay rate in S, but that's for convenience, the exponential one. There's still a bad influence of the dimension, but if the dimension is not super large, this will go quite fast to 0 as a function of S. And you can show that the holomorphic assumption is satisfied for a large class of parametric models, like parametric diffusion equations, parametric heat equations, where the input is the parameter, for example, that defines the diffusion parameter of the equation, and the output is the solution or a quantity of interest of the solution. So you can do now, to build such an approximation, you could do many things, such as classical interpolation or quadrature methods to approximate the integral giving you the coefficients, least squares. So although these three classical techniques will work very well if you know a priori in which polynomial space you should look the approximation. So you should look for the best approximation. So where the anisotropy of your function is known in advance. That doesn't happen. That is more challenging. You don't know in advance which polynomials you should activate, for example, in your least square search. In that case, you might resort to so-called greedy adaptive methods that I will not talk about in this talk, or to more recent techniques such as compressed sensing or deep learning. So that's what I will focus in here. And I'll quickly review the compressed sensing scenario. So your F is in practice is constructed by solving an optimization problem, which is a regularized, almost a regularized problem. So you might notice that the L2 norm of the residual here is not multiplied by an exponent, is not raised to an exponent 2. So that's why it is called the square root lasso problem. With the tool we call the so-called lasso problem. So you just solve an optimization given where sampling values is normally non-valuable values have this. It promotes sparsity in the coefficients. For technical reasons, to go in high dimension, you need to do weighted sparsity because that allows you to sample many less points. And then you put the output of this optimization problem, which is very nice, convex optimization. We have fast algorithms to do it into the approximation. That's how you build the compressed sensing approximation. And however, you need to pick an initial truncation. So you need to pick an initial ambient space, lambda, where then you will look for the best sparse approximation. So this paradigm was studied in a variety of papers, and also I worked in this field for several years. And this is the type of convergence, rigorous convergence guarantee you can give for a compressed sensing approximation. So if you're searched under the holomorphic assumption, given a fixed budget of samples, M, you can precisely quantify the decay rate of the approximation given by compressed sensing in L2 norm as a function of M. There's M tilde here because there's a bunch of log factors that you have to, that pop out from the theory. But you get essentially almost the same type of decay rate as best S-term approximation. That is the optimal thing you can do. There's only 2 here. Instead of 1 over D, 1 over 2D. For Chebyshev polynomials, if you're curious, actually, you can get to the D without the 2. What else here? And the ambient space is a so-called hyperbolic cross. And there's a technical thing to say here that the beauty of this index set is that it contains all so-called lower sets. So these are sets that of cardinality S that do not have holes in them. So there's much to say here, and I will not say much more. If you're curious, please check out. This is a shameless advertisement. This book by myself, Ben Atko, and Clayton Webster. There's a lot of approximation methods. So deep learning, this was a big detour into compressed sensing and high-dimensional approximation. People have done a lot of approximation theory for deep learning. That's a pretty topic these days, and pretty exciting too. So there are explicit like existence theorems, for example, for if your function is in a subgroup space, piecewise smooth, band limited, and so on. There are theorems, so-called universal approximation theorems, where you can formally prove that there exists a neural network that will approximate functions in this class with arbitrary accuracy in a suitable norm. So there's a lot of these theorems, and they're nice, constructive. You can explicitly show what the network looks like. And there's also available results for the holomorphic function class. However, these results do not address questions such as the need to actually train that network to approximate that class, or how do we train the network itself, or can we compare deep learning with compressed sensing? And what's more accurate, for example, since compressed sensing gives us the optimal convergence rate. That was what led us to prove this theorem, so-called practical existence theorem. So now you fix H is holomorphic in a Bernstein polyellipse. You fix now M IID Monte Carlo samples in the hypercube, and you can show that there exists an explicit class of neural networks that will be able to achieve the same convergence rates as those of compressed sensing in high probability. If you train, so the novelty now is that we provide a recipe for how you should train the network. And also there is data in the statement. It's not just given a class, there exists a network, but now given a class, given data, you can train the network that will be accurate and will actually capture the best S-term approximation rate. So this might be reminiscent of the square lasso. And in fact, the proof strategy, I can tell you more offline, is based on essentially linking deep learning with compressed sensing and essentially interpreting this training optimization problem as a square lasso optimization problem. So the gap between theory and practice here is that this problem will only train the last layer. That's why we're able to give a result, which is kind of explicit in the optimizer, and also will assume that you are optimizing this objective function. So there's not SGD here. We're assuming that the optimal network is achievable. And you can extend this, for example, for functions that take value in a Hilbert or Banach space. Okay, I'll skip the numerics. I'll conclude saying that, yeah, recap, we have seen, inspired by Ismail's 18th problem, we have seen how different variety of tools in the first impossibility theorems, there was, I would say, mostly linear algebra, really a bit of probability and elementary tools led us to prove some rigorous results about the limitations of deep learning. In the second case, combining more advanced results from compressed sensing, high-dimensional approximation theory, and deep learning approximation theory, we were able to show the potential of deep learning. So what kind of functions can deep learning approximate, as well as other techniques that are state-of-the-art. Of course, this is just 2 case studies. There's much more to be said. I just want to conclude with another shameless plug for people that are involved in my group. So these are some research directions that are going on right now, or some of them are more developed, some of them are just started. 3 of them are in the audience. So Alessio, Paul, and Aaron. So they're working on, so Alessio and Paul are working on problems linked to rating impossibility theorems for identity effects. Aaron is working on a lot of stuff. And one thing is compressed sensing with deep generative networks, which is a quite technical and an exciting field. So we do an analysis of that. With Weiqi, we use deep learning compressed sensing to approximate high-dimensional PDEs instead of functions. And if you're curious, run at the Monday seminar, CRM Applied Math Seminar by Weiqi this Monday, sorry, not Sunday. And with Sina, we're working on efficient compressed sensing algorithms. And we started working on a technique called deep algorithm unrolling to build architectures that are inspired by sparse recovery. With that, I will conclude with these references, and I thank you very much for your kind attention.
Thank you very much for the very nice talk. And a question from the audience. Yeah, if you want.
Yeah, I have a question on the second topic.
Yeah.
What properties made you choose the Legendre polynomials over other set of orthogonal bases like?
Right. Great question. Okay, in the talk, I'm only showing Legendre for the sake of, because otherwise this talk will be, it's already quite long. It will be even long. It was impossible to squeeze, but you can prove everything with Chebyshev polynomials too, for example. Actually, you get better results, but Legendre is just easier to present because the orthogonality measure is the uniform measure. So the samples will be uniform samples. With Chebyshev, you have to be, but essentially, whenever you have an orthogonal system, what will change is that you will have to sample according to the orthogonality measure. That's what changes. But you can extend this to other orthogonal polynomials.
Well, then, like, you've been studying these approximations, so like, did you apply them to some type of problem, like constructing?
Yes, so I did not have time to talk about applications, but okay, for example, here, this is a numerical result that I skipped. This is about an application to a parametric differential equation. So when I talk about parametric differential equation, it's something, this backup slide could be useful. For example, that's a parametric diffusion equation. Okay, so now, your physical variable is z. That's a typical diffusion equation, but you have some parameters, x, in the diffusion coefficient. So, and you could use that to model like heat propagation in a certain domain where maybe heat propagates differently in different regions. So you can do numerics in these kind of problems. What's nice about these problems is that you can provably show, we can rigorously show that the holomorphic assumption holds for these kind of models. So yeah, you can validate that with numerics. In this case, we compare compressed sensing with deep learning. This is a kind of a busy plot. There's a lot of course, lines. Let's see, slow. Okay, so the solid line is compressed sensing approximation. So here I'm plotting the number of samples on the y-axis and the accuracy of the approximation, in this case, the approximation of a parametric solution map to a 30-dimensional diffusion equation. There are technical things to say, but if you're curious, I can tell you offline. So, and all the other dashed lines are deep learning with different architectures, different hyperparameter tuning strategies. So if you're careful with the architecture, you can actually do better. So our theory tells us that deep learning can do provably as good as compressed sensing, but actually in practice, if you're careful with parameter tuning, you can do even better. Sometimes if you're not careful, you will do worse. So in a way, there's a lot of potential there, but as usual, like you have to be very, very careful about how you train the network to get the optimal rate. So that's what we observe in practice. Well, if you take training into account, there's no story. So compressed sensing is much faster. If you only count the feed-forward phase, well, still they're comparable. Still compressed sensing will be faster because it's just evaluating polynomials. Evaluating one, so compressed sensing is just a sparse polynomial combination. Okay, now it might look like I'm selling compressed sensing too hard. So what I will tell you also that if your function is not smooth though, so now this is a very smooth function, and compressed sensing typically is much more robust. If your function is not smooth, so maybe it has some discontinuity in the first derivative or something else, it will be much easier to get better approximation with deep learning because it's much more flexible. So that's where the catch is. We need smoothness for compressed sensing, but then life is easy. Like it's much faster, much faster to do the feed-forward phase too. But don't have smoothness in practice. You can see that it's easy to do much better with deep learning.
If there are no more questions, let's thank the speaker again.
Right.